So this is CS50, and this is the start of week 3. And you'll recall that last time we introduced a number of new ideas that we'll now start taking for granted as being already under our belt. In particular, we looked last time at debugging more generally. And recall that debugging is the process of removing bugs from your code, or removing mistakes from your code. And we proposed these 3 CS50 specific tools. In particular, Help50, which is a command line tool, something that you can run at your keyboard and actually run it before your own command, so that if you don't understand some error message from a program you're compiling or a command you're running, you can actually see some helpful output from CS50 staff. ePrintf, which by contrast is something you can put into your code like printf and print a message to yourself. And nicely enough, it's going to actually include the line number and the file name from which it came, so you can identify where some output is coming. And then lastly, Debug50, which is the most sophisticated of these programs. And Debug50, when you run it at the command line, followed by the name of your program in the usual way, it's actually going to open up what's called a debugger, a graphical user interface that CS50 staff put together that will actually let you step through your code, see variables, and generally understand it better. So we also looked at this in the context of Ovaltine in particular, and little Ralphie. And we looked at cryptography, the art of concealing information. And indeed, among the challenges in CS50, ultimately, if you choose to accept them, are things like implementing Caesar cipher and Vigenaire's cipher, cracking passwords. So indeed, those problems lie ahead and draw inspiration from this domain. And then we focused more technically on what a string is. So Zamyla, a name we keep taking for granted that a computer can express, Z-A-M-Y-L-A, as a string or a phrase in a program. But it turns out that underneath the hood, strings are a little more mundane. They really are just this grid of information. And we might draw Zamyla's characters boxed in like this. But if you think of what's inside of your computer itself, you have a whole bunch of memory or RAM. And inside of that RAM, you have Z-A-M-Y-L-A. But then this special character, what is this \0 used for? Why is there this seemingly strange character at the end of Zamyla's name? Anyone? Yeah. Yeah, to denote the end of the string. Because after all, if we were to have someone else's name here, if the next string I got is Maria, for instance, M-A-R-I-A, we need to be able to know where Zamyla's name ends and Maria's name starts in memory. Because at the end of the day, C, and programming in particular, isn't really all that sophisticated. At the end of the day, the only place you have to store things is your computer's memory or RAM. And each of these boxes represents a byte of memory inside of your computer. And so if all this is, so far as the computer cares, is a sequence of 6 alphabetical letters, the computer needs to be told or given a hint, as with this \0, which just represents 8 0 bits, as to where Zamyla's name ends and something else begins. And we use this as an opportunity to introduce, ultimately, command line arguments. So in particular, we've been writing programs thus far with just int main void. And void, we realized, signifies that a program takes no command line inputs. It can still call functions like getString and getInt and getFloat. But when you run the program, you can't put any additional words at the prompt after it if you've declared main as taking void as input, nothing as input. But we introduced instead this, int main, int argc, string argv, open bracket, close bracket, which means main can alternatively take 2 inputs from the so-called command line when you run it. It can take argc and argv. And what was argc? What was argc? Argc. Yeah, argument, yeah. Yeah, the number of command line arguments. Argc for argument count, so how many words did you type at the prompt? And argv means argument vector, which is another way of saying it's an array, a contiguous block of memory inside of which are all of the words themselves that you might have typed at the prompt. So this time, we're going to build on that. We're going to focus today mostly on ideas, mostly on algorithms, mostly on problem solving, and less on the lower level implementation details of code. Though we'll look at a couple of examples. So this, more generally, is what's called an array. If you think of your computer's memory as just a block of memory, block of bytes, and maybe it's byte 0, then byte 1, then byte 2, just because you can number them, certainly. If you think of them that way, this is kind of an arbitrary, generic data structure, if you will, a generic way of just storing things underneath the hood. Now, what do I mean by that, and why is this useful? Well, consider something like this. Consider having 8 doors, behind which are some numbers. And the goal at hand is to solve a problem. Find a number behind these doors. Now, unfortunately, you don't know in advance what numbers are behind those doors and where they are. Indeed, that's why the doors are closed. But you know that, say, the number 50 is somewhere behind those doors. So what do we do to actually find this? Well, let's go ahead and do this. Let me go ahead and summon up a brave volunteer, if you would. There's a CS50 stress ball in it for you. OK, come on up. You want to come on up over here? So we have not 8, but rather 7 doors here, even easier. So 7 to 8 the size. And what's your name? Derek Taylor. Derek? OK. David, come on up. Nice to meet you. All right. So here we have 7 doors. And the goal at hand for you is to simply find the number 50. Okay. How do we find it? What are you going to do?
Let's see. I need to find the number 50 and it's behind one of these
It's
doors.
behind one of these doors, I think.
All right. I'll just try a door.
Try a door. Not the door. So 16 turns up. OK. Stress ball gets 1 step away. Try another. 42. Answer to life, the universe, and everything, but not this question. 50. OK, very well done. So a round of applause, if we could, for Derek here. Very nicely done. OK, and let's pause for just a moment. What was the algorithm? What was the set of instructions that you used to find the number 50?
Just try and see if I could find any sort of arrangement, but otherwise, try random doors.
OK, so try random doors. And indeed, given no additional information from me, that's the best you can do. Just try random doors. Or if it's a little easier, just go left to right or right to left. But random is perfectly equivalent to all of those algorithms because you don't know anything necessarily a priori. So how about for 2 stress balls? Find the number 50 this time. But the additional ingredient is that we have taken the time in advance to sort the numbers behind these doors. Does that change your thinking in any way? Good. So good challenge. He doesn't know if we've sorted from left to right or right to left, left to right. So generally, a computer scientist, when he or she says sorted, would say left to right.
Left to right,
but reasonable question.
Left to right increasing? Or
left to right increasing, yes. It would be left to right in any way. 16, not 50. So what are you going to do?
Well, let's see. I know these have to be less, so I can remove them.
Good.
Contention.
42 is still not 50. And to the right. Very well done for Derek. OK, come on. OK, they're less impressed that time. So what did you do, though, that second time that was actually more effective? I mean, frankly, at first glance, it looks like this approach was just as fast or just as slow as your first approach because it still took you 3 steps.
So what I did was, since you told me that it was sorted left to right increasing, I decided to look at the middle number first to see whether it was greater than or less than
Good.
the target number.
Good.
And since it was less than, I knew that all of these 3 values
Wonderful. And indeed are smaller by design. And so you can throw half of that problem away, much like in week 0 when we tore the phone book in half. You can throw half of that phone book away as well. All right, so thank you very much for finding us the number 50. So this is something that we did see indeed in week 0, and it's what we would generally call binary search, or more generally, just a divide and conquer algorithm. But today what we start to do is to assess just how much better this actually is and how we can go about finding things more programmatically. So what Derek could have tried is what someone would generally call linear search. And as the name suggests, linear meaning line, you can just kind of solve a problem from left to right. And indeed, while Derek did take a random approach, it would have been functionally equivalent for him simply to go left to right or right to left and find the number 50. It's indeed there. So let's introduce some pseudocode for this. And there is no one right way to implement pseudocode. Here is one of the most succinct ways I could come up with for expressing this kind of left to right approach, or equivalently right to left. For each element in the array, if element you're looking for, return true. And so this is a very common paradigm in programming, to just say something generally like for each element in an array. And the implication is that you would generally go left to right, but it's equivalent to go right to left. And if we indeed see at some location in that array of boxes, the element we're looking for, we can just return true. And yet here I have return false. But the indentation, so to speak, is very different. Why have I aligned return false with the for loop here all the way on the left, as opposed to it being aligned in the middle or one line deeper? Yeah?
In order to denote that all the indented elements are within the for loop.
Yeah, in order to denote that all of the indented elements are within the for loop, so it doesn't strictly matter how much you indent. And indeed, in some languages, see among them, it doesn't matter that you indent at all. But for the sake of good style and readability, we've indented this to convey to the human especially that this if is only applicable when you're inside of the for loop. This return is only applicable when you're inside of this if condition. And this return false really only happens as the very last step in this program if nothing else actually returns a value. So only if return true happens does this program say, yes, I found the element you're looking for. And you can think of this, therefore, as the sort of default case. Now, just to toss it out there, why would this be wrong? Let me go ahead and temporarily change this program to be a more familiar if-else block. So why is this seemingly logically fine? It's a valid puzzle piece, if you will, a la Scratch. But this program is now incorrect. Why? Yeah? Once you hit, it's automatically going to come out of the for loop. When exactly? When will this come out of the for loop? Good. So it's going to return false if the first element isn't what you're looking for. Insofar as for each element in an array kind of implies that you should be looking from left to right or right to left. The first question you're asking yourself when looking in that first element is this the element you're looking for? If it is, great, you're going to return true and your answer is correct. But if it's not the element you're looking for, you're executing else return false, immediately saying, no, the element I'm looking for is not here. But when really the only question you've asked is the element I'm looking for the very first in the array? And so indeed, this would just be logically incorrect because you might as well not look at any of the array if you're only looking at that very first element. So not what we intended. So indeed, that original pseudocode is just fine. So alternatively, there's something called binary search, which Derek actually used intuitively for his second approach, where he was told in advance that the array is sorted numerically from left to right. This gives him more information, much like I had in week 0 when I searched a phone book that I knew was alphabetical. And you can write this algorithm in any number of ways, too. I kind of borrowed the spirit of our Mike Smith algorithm from week 0, and I propose this. Look at the middle of the array. If element you're looking for, return true. We just get lucky if it's smack dab in the middle of the array. Else, if the element is to the left, because the element you're seeing in the middle is too big, then search the left half of the array. Else, if the element is to the right, as it was in Derek's case, search the right half of the array. Else, return false. But there's no go-to instruction here, and there's no line numbers. Recall from week 0, when we searched for Mike Smith, I deliberately numbered all of the lines, and then I said, go back to step 2 or 3, I think it was. Here, I seem to be cutting a corner. I'm just kind of waving my hand and saying, search the left half of the list, or search the right half of the list. But what algorithm should we use in either of these cases? How do you search the left half of a list? How do you search the right half of a list? How do I do this? Well, where do I have an algorithm for searching? Well, we saw one a moment ago. I've already gotten my toolkit, so to speak, linear search, so I could certainly use that. But sort of cyclically, or sort of confusingly, I also have this other seemingly fancier, faster algorithm called binary search. And yet I'm in the middle of defining binary search with my pseudocode. And yet here I am sort of trying to define myself with myself. Right? You can't get away with this in English. If you're asked to define an English word and you use the word in the definition, usually a teacher or someone in a conversation will sort of verbally slap you on the wrist because you're not answering the question. And yet somehow, in programming, you can get away with this. Somehow you can get away with defining a problem with a solution like this and then using that same solution inside of your solution because something is changing. This line here, search left half of the array, and this line here, search right half of the array, is not equivalent to asking the same question again. Is this element in the array? What changes when I either search the left half or the right half that makes this acceptable? What's that? Yes, that's the key ingredient. Insofar as search left half and search right half imply search in the same way, but search a smaller problem, this problem will eventually stop. You're not going to get stuck in an infinite loop, so to speak, because eventually you can't have something in forever. You're eventually going to end up with 1 or 0 elements, at which point the answer is going to be no, return false, it's not here, per the else condition. But these sort of reflexive calls, or inductive, or more properly here, recursive calls, the new buzzword for today, means for a function, or in this case pseudocode, to call itself, to use its own definition again and again and again, which is bad instinctively unless you keep doing it on smaller and smaller problems. And so this is a general principle, actually, that we're going to be able to leverage ultimately, not only for searching, but also, as we shall see, for sorting. So let's go ahead and let me share actually how this example went last year. We're fortunate to capture sort of memories on film, and it thought it'd be fun to share this when one of your predecessors in the class came up, was asked the exact same question, find us the number 50, but it didn't quite go as well as we hoped. Let's take a look at 2014. All I want you to do now is to find for me, and for us really, the number 50 one step at a time. The number 50, and you can reveal what's behind each of these doors simply by touching it with a finger. Damn it. OK, so that didn't really demonstrate anything that year. So we tried again, this time saying, all right, this time the array is sorted. What are you going to do this time if you want to find the same number 50, but the array is now sorted? Thought I'd share this. The goal now is to also find us the number 50, but do it algorithmically and tell us how you're going about it. Okay. And if you find it, you keep the movie. If you don't find it, you give it back.
Man. We have the same. Okay. So I'm going to check the ends first to determine if there's... Oh.
Okay. OK, now I feel a little bad, because clearly we used to give away movies, and now we give away stress balls. But no one really has DVD players anymore, so it's OK, probably. And then let me share one other clip back from our SD days many years ago, when Sean, who since graduated, came up, was asked the same question. And so, Derek, you are in this wonderful history of students who have tried this demonstration. This was, as you can see, before we had touchscreen technology, so we had sheets of paper up on the screen. But the idea was the same, and Sean is perhaps one of our favorite memories insofar as he, too, was asked to solve the same problem in his way. OK, so your task here, Sean, is the following. I have hidden behind these doors the number 7, but tucked away in some of these doors as well are other non-negative numbers. And your goal is to think of this top row of numbers as just an array, or just a sequence of pieces of paper with numbers behind them. And your goal is, only using the top array here, find me the number 7. And we are then going to critique how you go about doing it. All right. Find us the number 7, please. No. 5, 19, 13. It's not a trick question. 1. At this point, your score is not very good, so you might as well keep going. 3. Go on. Frankly, I can't help but wonder what you're even thinking about. So only the top row. So you got 3 left. So find me 7. $17. All right. So we don't ask people to search for 7 anymore. But this invites the question, how are we allowed to have that assumption, right? I've been assuming in week 0 that the phone book was alphabetized, and therefore I can find Mike Smith really fast in logarithmic time. And we were just assuming a moment ago that we could find the number 50 super fast because of divide and conquer again, but only if that array were sorted. Indeed, Derek technically just got lucky insofar as he found 50 the first time in 3 steps, but it could have been as many as 7 steps because it was indeed a random algorithm, or even if he had used linear search. So suppose we want to actually sort something. So these are still used on campus sometimes. So these are blue books for exam period. And suppose that we're at the end of a semester and a bunch of students have written their names on these things. And so A's and B's and C's and D's. And suppose that they're handed in at somewhat random times. So there's always that kid who hands in his or her exam at like an hour into the 3-hour exam. And then most of them come in around like 2 hours, 45 minutes. And so therefore, they're all in this pretty random, arbitrary order like this. Actually, if I just put them down like that, they're not really random at all. And so they're just in some random order. And the goal at hand ultimately is for the head TF, for instance, or the professor to actually sort all of these blue books and come up with an alphabetical order so you can make sure that everyone has actually submitted on time. So how do we do this? Like, what is the algorithm with which to do this? Because indeed, if he or she, the professor later, wants to find a certain name of the alphabet, like Smith, it'd be nice if they don't have to sift through all 26 or all 100 or all 500 blue books. They can just jump roughly to the middle and then divide and conquer and find Smith thereafter. So can we get one volunteer to come up and propose how to sort? You want to come on up? Come on up. What's your name? Allison. Allison. All right. Come on up. So if you've ever sorted something before, now's your chance to show that off. Allison. All right. So here are a whole bunch of blue books. And I've just arbitrarily written not names, but first letters of the alphabet on them. So go ahead and sort them.
I start with a letter, and if this is before that, I just put it on top.
OK, so that's X and L. Gotcha.
And because Z is after,
there's
I
Z.
put it below, and D is here.
OK. So you seem to be taking them one at a time and just dealing with the problem then and now.
Yes.
OK, so that's J. What happens next? J. You want to? OK, that's K. K, L, good. B, that's easy, on top. A, even easier, on top.
Am I going to finish this entire thing?
Yes, we need 13 more, give or take.
OK.
M, N, O. I didn't do a very good job there. U, V, OK, definitely not good. Y, it's good, goes toward the end. R, a little harder. But this is actually a good situation for us to be in because you keep going. I'll keep talking. So even as Allison is sorting this, she's dealing with each of these blue books one at a time. But notice what's happening to her right hand. There literally is more and more work, it seems, happening in her right hand because as she encounters R or now W, not only does she need more thought, she also needs to do more flipping to actually find the right spot for W. This is H. She's doing the same thing again. So it feels like the algorithm has started to slow down. At first, it was pretty easy to just make a short list. But now that the list is getting longer, it feels like she's fixing a lot of work. Or finding a location is getting harder and harder. Or at least taking longer and longer. Maybe the alphabet itself is not that much more difficult. Now we have I. I can only stall so much longer. G.
Sorry.
No, it's fine. E, good. OK, so it's getting a little easier because we're at the beginning. Whew. Sorted. So what were you thinking? What was that algorithm?
It was just take a letter, take another letter, and then test to see if the letter is before or after.
OK,
and then
good.
Put it in the correct place, like on either side.
Perfect. So a perfect way of thinking about this as well. So thank you so much.
Thank you.
Very nicely done. And suppose the problem's a little harder. I'll do this one myself here. But suppose we have some playing cards. And these are the type that probably everyone here can see. So here is a standard deck of cards, including the jokers, which we won't need. How do you go about sorting things like this? I don't know if, actually, I didn't think in advance. I should have shuffled these. So if you want to shuffle these cards, this is not going to end well. OK, so suppose we have all of these cards nicely shuffled here. And I have before me a big problem, a big pile of cards. And the goal, for whatever reason, you want to just start the game or you like to be orderly, is to sort the cards. What's your algorithm going to be for sorting these cards? What might you do? No? Yeah. Yeah, do them in piles based on the number. OK, so here's the number 2. So you want me to make a pile for all the 2s? OK, so we can do that. So here's a pile for all the 4s. And let me make myself some more room. So we can put 2s here, 4s here. Here's a 3. So I'm going to put this in between the 2 and the 4. Here's a 5. I'm going to put that over here. And if I jump around, here's a jack. So this is going to go way over there. 7, 8, 6 can go over here. Here's another 4. So I can put it here. and I can sort of bucketize all of the cards. So this is good intuition because it makes a pretty big problem, 52 cards, a little more tenable. You can just now flip through all of the cards one at a time, or whatever you encounter first, and just drop it in the correct bucket. But that's, of course, not going to get you to the end. Let's assume we fast forward to the ending, and now I have these 13 piles from ace all the way up to king. What do I then do? What's step 2? So I want to stack them, so I can take all the 2s, all the 3s, all the 4s. And I didn't specify earlier, one of the things that complicates this problem with cards is that you have different suits. And so if you really want to be nitpicky, maybe you want to keep all the suits the same, which is like a nested sorting problem of some sort. But this general idea of bucketizing in this way is good intuition, but it clearly takes some time. I mean, enough time that I'm not going to sort of drag this out by sorting all of those cards myself. And therein lies the point, though. Even though in week 0 with Mike Smith, we had that sorted phone book, and even though a moment ago Derek, albeit with a few numbers, had them already pre-sorted, sorting takes time. And even when we were just sorting the blue books alphabetically, even though it felt pretty fast, pretty obvious, it starts to drag eventually. And God forbid there were more than 26 books. Maybe there were 260 books, or 600 books, or 2 million books, or web pages, or database records. Any number of problems in this world now require sorting sometimes, whether it's on Google or Facebook or your own computer. Feels like we need a good algorithm for actually doing that sorting. So how can we go about doing that, not just with blue books, not just with cards, but more generally? Well, let's try to frame the problem first with a simpler world. In fact, we can generalize blue books and playing cards is really just numbers. Or some piece of data that there's a defined order or sequence to them. And suppose I have these numbers here. How do I actually go about sorting this many numbers? Well, for this, and this will be our last chance for audience participation here, I need 8 brave volunteers to actually come on up. All right, so 1, 2. OK, this is what everyone's been waiting for. 1, 2, 3, 4, 5, 6, 7, and 8. Thank you. Come on up, and I will meet you over here. All right, come on over here. If you want to grab 2 music stands. OK, so let's go ahead and turn these around like this if you could, as though the music's going to face the audience. OK. All right, and let me go ahead and give you sheets of paper, and then we'll resume here. All right, so here is our 8th music stand. And what we have here is 8 pieces of paper. And each of you guys is going to take on the role of a certain number right now. So I'm going to go ahead and give each of you a number in sorted order initially, but that would be too easy. So if you don't mind, let's go ahead and arrange yourselves behind these music stands in the same order that you see on the screen. So on the left end here near me should be the number 4, then 2, then 6, then 8, good job, then 1, then 3, then 7, then 5. All right, so now, and you can put the numbers on the music stand there, but just move them with you as you go. So now the question is, here is a seemingly random list, in just some order I came up with, somewhat arbitrarily, and I want now to sort my list. How do I go about doing it? What would you propose? The goal is to get from 1 to 8. What are our possible approaches here? Oh, you want to? Sure. OK. We'll just do it over here.
You pick out the smallest number.
OK.
Take it, shift everyone else down, put the smallest number in the first place.
OK, good.
So on and so forth.
So let's go ahead and do that. So let's see. And for those tuning in at home, what's your name again?
Allison.
Allison and?
Alex.
Alex?
Adam.
Adam?
Brandon.
Brandon?
Joseph.
Joseph?
Vicky.
Vicky?
Arpin.
Arpin?
Derek.
Derek. OK. So now, because that all just was too much to absorb, number 1 is now the first smallest element according to the proposed algorithm. So what are we going to do exactly with number 1?
He's going to take it up. We're going to shift down.
OK, good. So pop back if you would. You guys are going to shift 3 places this way, and we're going to insert number 1 at the beginning of the list. All right, so what's the next step, just to be clear?
Number 2 is going to pop up.
Good.
I'm going to shift down. Number 1's in the same place.
Good. So we find the next smallest element, which happens to be 2. We insert him at the beginning of the list here. And now we move on to the number 3 problem. Excellent. So pop back, shift, and insert. Good. 4, we got lucky, so we don't have to do any extra work here. So that's a freebie. Now we look for 5. Oh, there's 5 at the end. Good. And now 6, we got lucky. 7 and 8, we need to fix that. OK, good. So I like this. It felt pretty fast, though to be fair, the list is pretty short. but we were doing kind of a lot of work, right? In fact, that was perfect, the fact that number 1 was all the way over here, because we shifted 3 humans. And can you guys reset for just a moment? Let me propose an alternative approach. So if number 1 is in the middle here and really belongs all the way there on the left, we went to great lengths, it seems, to shift all of these volunteers to the left, which is a lot of steps. Because at the end of the day, let's assume for today's purposes that a computer can only do one thing at once. So even though all of you humans moved pretty quickly, that was really like one of you moved, then the next of you moved, then the next of you moved, then the next. So that was like 4 total steps just to put number 1 on the end there. Let me propose this. 1, can you pop out again? Now this list, so far as I'm concerned as the computer, is perfectly random from the get-go. So why do I even care that you guys move? I haven't even looked at the rest of these elements yet or done anything with them. Why don't I just evict number 4, where number 1 belongs, if you want to go over here? And if the list is already randomly sorted in the beginning, well, then fine, 4, you're going to go over here. So I've made the problem no worse, but I have made it slightly better by putting 1 on the end. Now I'm going to go ahead and select the next smallest element again. 2, I got lucky. Now I'm going to look for the next smallest element. 3, indeed, is the smallest. So let me do the same thing. 3, if you could pop back. 6, you're out of there. And notice that we're doing less work. Now, the humans are moving a little farther physically, but that's fine. The computer can just move values around in memory pretty fast, but I've moved fewer of you. So this is a slight optimization. It turns out this isn't fundamentally better, as we'll see. But it's this instinct that you should appreciate of trying to do the least amount of work possible, because otherwise it's going to add up. Let's try another one. Well, let me clarify one thing then. So what am I doing on each iteration of this algorithm? As you suggested, I'm selecting the smallest element. But the only catch is, if I'm next looking for the next smallest element, that's going to be 4. But I'm only sure that it's 4 once I get to the end and realize, yep, that was the smallest element, and then I act. So once we fix that problem, if you guys want to switch, I start again over here, and I have to find the next smallest element. And let's see, 8 is pretty big. 6 is smaller, good. 7, not smaller. But only once I get to the end do I realize, oh, here's the smallest. So in short, to find the smallest element, as you proposed again and again, I have to keep going through the whole list, because it might be all the way at the end. We humans have the advantage of just kind of looking, sort of taking a step back and saying, OK, this is obviously unsorted. I know where everything is. A computer can only look at one number at a time, one element of an array at a time. So let's try a fundamentally different approach. If you guys could reset to your original 8 locations, let me propose that we just looked at an algorithm we'll call selection sort. Selection sort insofar as you iteratively, again and again, select the next smallest element. Let's now do an approach that we'll call bubble sort, which has sort of the visual effect of numbers bubbling up over time as follows. You know what? I'm just going to look not at the whole list, because it felt like that was creating a lot of work for me. I'm going to look at 2 numbers at a time, 4 and 2. Are these in order or out of order? Obviously. So they're out of order. So you know what? I don't care about the rest of the problem. Let me just swap you 2. All right. Now let me take one step, look at 4 and 6. In order or out of order? In order. So I'm going to leave it be. 6 and 8, in order. 8 and 1, not in order. So let me swap that again. 8 and 3, out of order. Let me swap that again. 8 and 7, out of order. Let me swap that again. 8 and 5, out of order. Let me swap that again. And now what has happened? Is the list sorted? Because I fixed all the pairwise mistakes. So obviously not, but is it better, the list? Why is it better, Derek?
Because now you have one less element to worry about.
Yeah, exactly. 8 bubbled all the way up to the top, if you will. So now he is effectively done. And frankly, every other number that's smaller bubbled one step closer to its position. So we've taken one big pass through this to solve at least one of the problems. And now maximally 7 problems remain. So let me go back to the end here. And let me look at pairwise. 2 and 4, you're good. 4 and 6, you're good. 6 and 1, let's fix that. 6 and 3, let's fix that. 6 and 7, we're good. 7 and 5, let's fix that. And now I can ignore number 8, because I know the end of my list is sorted. So now I've improved it slightly. 7 has bubbled up to where he needs to be. I just have 6 problems left to solve at most. So now I look again. 2 and 4, you're good. Oh, 1 and 4, let's swap that. And notice 1 is moving closer to the left of the list. 4 and 3, let's swap. 4 and 6, you're good. 6 and 5, you're not. But now I fixed 6, and I can stop here, leaving me with just 5 potential problems. And then you can see where this is going. 2 and 1, let's swap. 2 and 3, you're good. 3 and 4, you're good. We already solved these problems, so let me go back. And now 1 and 2, you're good. 2 and 3, you're good. 3 and 4, 4 and 5, 5 and 6, 6 and 7, 7 and 8. What do I know now as the computer? What's that? It's sorted. Why?
Because everything's in order.
Everything is in order, but what does that mean? We humans can see that, but the computer can only look at individual values at a time. It can't take a step back and say, yep, sorted.
There were no two pairs that conflicted.
Good. At a lower level implementation detail, I did no swaps. There were no two numbers that were out of order, so it would just be foolish of me and wasteful for me to bother doing another pass, because assuming the numbers are not changing on their own, I'm just going to do the same thing again and again otherwise. So I can just stop. And indeed, the bubble sort allows us to stop like this. Let's do one last approach, if you could. Let me toss the starting points on the board again. Let's reset one last time to this. And let me draw inspiration actually from the approach you took with the blue books, which was a little different from how we began, which was recall that you took the problem on your left hand and you just dealt with it one at a time. You didn't go sifting through looking for A. You didn't go sifting through looking for B. You didn't go sifting through looking for C, which would really be the analog of what you proposed a moment ago. Instead, you just dealt with each problem as it came. And this is our third and final algorithm for sorting called insertion sort. Take each problem one at a time and just deal with it then and there. Don't postpone. So here's 4. You know what? Done. I now claim that this list, which we'll visually make a little separate, is sorted. So I'm going to mentally divide my list into a left half and a right half. And now I just claim trivially, almost silly, this is sorted. Because it is. But now the right half of my list remains. So let's go ahead and do this. So number 2, OK, where does this belong? So if you want to go ahead and pick up the number, the stand can stay. Number 2 goes where? Here's my left list, and we'll make a little more space here just to be clear. It goes over this side. So what has to happen? So this time we do need to shift you over. So let's take 2 out. Let's shift 4 over. And now we won't move the stand. We'll just assume now that my left half is of size 2 and the right half is of size 6. But now the left half of the list is still sorted, but it cost me a little bit of work. I had to move 4 over. All right, let me deal with 6. Where does 6 go? Phew, it's already in order. I don't need to shift anyone. Where does 8 go? Phew, doesn't need to go anywhere. It's already in order. Uh-oh, 1, where does it go? Now we incur a good amount of cost, so let's do this. Where do you go? 1 shift, 2 shift, 3 shifts, 4 shifts. Feels, as bad as our original approach, but notice I only have 4 more problems left. I don't have to keep going back through the list. So where does 3 go? All right, let's pop you out, shift you in there. Let's 7, we got a little lucky. Let's pop you out and insert you right where you belong. And then 5, you belong a few shifts over. So let's shift 3 of you. And then done. All right, so let's give all of you a stress ball and maybe a round of applause. And let's see if we can't tease apart what just happened here. All right. And then you can exit stage left if you'd, right if you'd like. All right, thank you. Derek, you're really racking them up here. All right.
I'll need them.
All right, thank you. All right, so sure. So what was the point of this exercise, and how do we actually now get to a decision point where one of these is the way to go? So in bubble sort, recall that the key was to do something again and again until we did no swaps, at which point we could conclude that the list was sorted. So let's do exactly that. Repeat until no swaps. And then let's give ourselves a counter just to make things a little more methodical and say, for I from 0 to n minus 1, rather n minus 2. Why? Well, the end of the list, recall, is at n minus 1, because if you have a list of size n, the beginning's at 0, the end is at n minus 1, and so 1 shy of the end is going to be n minus 2. So we want to do this up through the second to last element. If the ith and the ith plus 1th elements are out of order, so if left hand and right hand are out of order, swap them. And repeat this again and again and again. And thanks to that outer loop, we're going to do it again and again and again until we have no such swaps. And now, to be clear, why this n minus 2? We want to make sure, as we're sort of walking down our row of volunteers, that my left hand does not actually point at the last human on stage, because then where would my right hand point? There's no person to beyond that point. So this then is bubble sort. Now let's propose pseudocode for our other algorithm, selection sort, wherein we walked through the list iteratively, trying to select on each pass the smallest element and putting it into its place. So for I from 0 to n minus 1, we're going to do this from beginning through the end. Find the smallest element between ith and nth minus 1th element. Swap the smallest with that ith element. In other words, walk through the list, find the smallest, put it on the end. Walk through the list, swap it with the second to the end. Walk through the list, do the same, do the same, do the same, each time grabbing the then smallest element. And then lastly, we had insertion sort, whereby we iterated through the list, but we pretty much dealt with every element as we encountered it. So let me propose this pseudocode here for I from 1 to n minus 1. So let's just assume that the very beginning of the list is sort of trivially sorted, no matter what number he or she is, because if that left side of the list is of size 1, it is indeed sorted. And indeed, let's call the 0th element through the I minus 1th element, wherever we are, the sorted side. So essentially call the left the sorted side, and you can think of the right-hand side as the unsorted side. Remove the ith element, whatever element you're dealing with, and insert it into the sorted side in order. In other words, just walk through the list one at a time, plucking out elements, and then forcibly insert them into the sorted side of the list, making room, as our humans did, for that list by shuffling everyone over. This then was bubble sort, selection sort, and insertion sort. But which to choose? So let's introduce now an answer to why. Not just what these things are, but why you might use one over the other. So the running time of an algorithm might be the number of seconds an algorithm takes to run, or the number of minutes, or the number of steps, or the number of comparisons. It doesn't really matter what your unit of measure is, so long as you're consistent, whatever feels the most expensive or useful to express. So let's consider an example like bubble sort. If we want to consider the efficiency of bubble sort and make a claim as to whether we should or shouldn't use it because it's good or bad, let's consider it a little formulaically, so a little mathy, but pretty generically. So if there are n elements to sort, and a computer scientist, recall from week 0, will generally just call n the size of his or her problem. N is the number of numbers to sort, or humans to sort. How many steps is it going to take to sort that many people? Well, when I had 8 music stands and 8 people here before, I considered a pair, a pair, a pair, a pair, a pair. And so if there were n humans up here, or let's speak concretely, 8 people initially, how many pairs of people did I consider in my first pass? Say again? 7, right? Because if you pair the first and the second, then the second and the third, then the third and the fourth, that gives you n minus 1, generally speaking. You can't make 8 pairs out of 8 people. You can make 7 pairs if you keep walking through the list. We're not doing permutations. We're just doing adjacent neighbors. OK, so that might generically be n minus 1 total steps for the first pass of my algorithm. But the upside of that was that our 8th volunteer, number 8, bubbled his way all the way up to the end. And so with bubble sort, I didn't need to consider him again. The biggest number bubbled all the way up. And so that was done. So how many pairs did I need to consider the second time through bubble sort? 6, or more generically, n minus 2. And then dot, 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 until there was just one pair of 2 people left. So I'll just do plus dot, 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 plus 1. Now, you might recall from like high school especially, at least my math or physics textbooks always had a little cheat sheet for like what these kinds of recurrences or formulas add up to. Does anyone recall what this one adds up to in a math book? Or just mathematically? So if we actually do this out, it's the same thing, beautifully, as n times n minus 1 over 2. And that, of course, if you multiply things out, it's just the same thing as n squared minus n over 2. And that, of course, feels like it would just multiply out to this. So in other words, if asked, what is the efficiency of bubble sort, or what is the running time of bubble sort, to sort n elements, you might sort of impressively say, well, it's n squared divided by 2 minus n over 2. But what does that actually mean? Well, it turns out that when talking about the efficiency of algorithms, you should really generally care about the component that has the biggest order of magnitude, the number that contributes the most to the total cost. And by that I mean this, which is obviously bigger, n squared or n, assuming positive values of n. So n squared, right? Especially as n gets bigger, n squared is going to get even bigger than n. So you know what? I'm just going to kind of propose, let's just ignore the n minus 2, because as n gets really big, the dominating factor really is going to be n squared. And for that matter, the n over 2, like who cares about the over 2? N squared is kind of the essence of this formula right now. So what does that mean? Well, let's just do a concrete example to convince you of the fact that we can cut a little bit of mathematical corner here and only care about the big number for the following example. This is proof by example, which is not a proof of anything. It's just really to paint a picture of why we do this intuitively. So suppose that there are 1 million volunteers on stage, or 1 million numbers that we want to sort, much bigger than 8. Let's plug this in. So if the total cost of bubble sort is n squared over 2 minus n over 2, let's plug that in. So that's 1 million squared divided by 2 minus 1 million divided by 2. So if we multiply that out, that is 500 billion minus 500,000 big numbers, but when you multiply that out, I mean, my God, 499,999,500,000. I mean, to my sort of my own eyes, that's pretty darn close to 500 billion in the first place. Why don't we just call it 500 billion? So n squared, in other words. So again, this is not a formal proof of anything, but this is why, especially as n gets bigger, that lower ordered term, the minus n over 2, just matters less and less and less in absolute form. And so we'll generally say that something like bubble sort, its running time is on the order of n squared. Big O is actually formal computer science notation for on the order of. And it has a formal mathematical definition. But for us, we'll consider it really to be an upper bound on the running time of this algorithm. So an upper bound on how long this algorithm might take given n steps. So big O itself is a formal notation. And we'll see it in a number of different contexts. Depending on the algorithms we talk about in class, we might say that the running time of an algorithm is on the order of n squared, which is pretty bad, pretty slow. 500 billion sounds like a lot. Well, maybe it's a little better, on the order of n times log n, and more on that some other time later. But on the order of n was pretty good. If there's n elements, it only takes you roughly n steps. Maybe it's even better, big O of log n, or really best would be big O of 1. Just takes 1 step, or 10 steps, or 100 steps, but a constant number of steps is what big O of 1 represents. And there's any number of other formulas we could use, or equations to express the running time of algorithms, but many of the algorithms we'll look at in CS50 certainly fall into these categories. So let's take an example. What is the running time? What algorithm has the running time of big O of n squared? Well, bubble sort, for one thing. And it turns out selection sort. And it turns out insertion sort. All three of those algorithms actually have the same running time, even though they're fundamentally different in execution. But they do share a commonality. All of them are comparison based, right? In each case, did we actually compare values, either adjacent, or we would look at a number there, compare it to a number here, and then decide whether or not to do a switch. So they were all comparison based, and all of them, frankly, involved quite a bit of movement or walking, either on my part or the humans, volunteers' part. For instance, in bubble sort's case, I had to walk through the whole list, sorting elements pairwise, like this. But that wasn't enough. I then had to do it again and walk across the stage. And then I had to do it again and walk across the stage. And this is what n squared feels like. And even though the problem was getting a little smaller as the big elements bubbled up, mathematically, even that algorithm, it's kind of essentially like doing n things, looking at n people, n times, iterating n total times, which is roughly n times n, or n squared. It's just going to add up a lot. So what about, OK, selection sort? What did I do in selection sort's case? Here it's even more obvious, perhaps. To find the smallest element in a list, I have to look logically at every element before I can confidently conclude, yes, I have found the smallest element. Once you find it, you can plop it at the beginning, and that's easy. But then you have to find the second smallest element. And even though we humans could kind of eyeball things and realize, oh, 2 is the next smallest, you don't know that as the computer unless you look at every element. Ah, I found 2. And then you can put 2 where it belongs. So again, there's this walking back and forth. And if you're going to walk as many as n steps, and you have to do this n times, 1 for every element, that too is n times n. And insertion sort, same damn problem, even though it's sort of logically different, the algorithm. In insertion sort, beautifully, I only move 1 step at a time, and I never turn back, because I just deal with, as you did for the blue books, each problem 1 at a time, never again backtracking. But where was all the work happening? In the shifting of humans. Now, technically, you guys helped out by doing the shifting yourselves. But if I'm the computer, it actually would have been like me tiptoeing back, shifting, 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 inserting, shifting, shifting, shifting. So again, in the worst case, I might have had to shift everyone all the way over to make room for someone. Because in the worst case, what's the worst possible input you might get to a sorting algorithm? What input would create the most work for you? Backwards. If the list is perfectly backwards, every darn element is out of place, which means you have to traipse back and forth to insert or to select or to swap all of those elements that many times. So in all of these cases, they are not numerically identical. Some of those algorithms might take fewer steps than others in totality, but they are all on the order of n squared for the reason that they're all involving comparisons as many as n times n times. All right, what about an algorithm that's big O of n? An algorithm that only takes n steps. We've seen one. Derek showed us one. What's an algorithm that takes n steps? Derek, hopefully? A random search, kind of, sort of. It's a little harder to put a number to, because depends what you mean by random, because if you have random with repetition, such that you're checking foolishly the same elements again and again, it can actually add up to more than n steps. So not random, but yeah. Binary is even better. Hold that answer. You're about to be correct. Linear search, right? If you just blindly go from left to right or right to left looking for some element, that is on the order of n steps, because you are just doing foolishly unnecessary work. If you go beyond the end of the list or beyond the beginning of the list, you only need n steps for linear search. But what if you want to instead find an algorithm that's logarithmic? What algorithm that we used might be logarithmic in nature? Binary. So binary search, as Derek proposed once we knew the list was sorted, was an alternative to that. And constant time, what about this? What's an algorithm, maybe independent of today, that allows you constant time running time? Well, it could be anything. How about hello world? The say block, or a printf, like that, if you can just say a whole phrase at once. Or maybe just adding two numbers together is like one step. No matter how big the numbers are, still just takes one step to add them all together. Depends on some of the lower level implementation details, and even printf or the say block has multiple characters. So we'll actually come back to this in the future as to what it really means to be a step. But anything that takes a constant number of steps, checking an if condition, returning a value. Statements generally might be, broadly speaking, just constant time, but we'll see contradictions to that before long. So let's take a look at two other symbols, this one being a capital omega symbol. And this omega symbol is the opposite, really, of big O. Big O is an upper bound on the running time. In the worst case, how many steps might it take to find an element in a list of n elements? N steps, so big O of n. Bubble sort, selection sort, insertion sort, they're on the order of n squared. But what about the lower bound? Especially when you get lucky, in the best case, so to speak, how few steps might you solve problems with? So for instance, if we consider the same formulas, but this time with capital omega, what's an algorithm that no matter what takes n squared steps, even if, for instance, the list is sorted? So suppose our 8 volunteers here were already 1, 2, 3, 4, 5, 6, 7, 8. Which of those algorithms would still have required n squared steps? So not linear search or binary search, because those are much lower, but insertion, bubble sort, selection sort. Well, what about selection sort? Even if the list is already sorted, how do I find the smallest element? I'm lucky and it's right here, but I don't know that yet, right? To know that, I have to confidently walk the whole list and realize, well, that was a waste of time. 1 is indeed the smallest element. It's sorted. How do I find the next smallest element? Start at the left, but you can ignore number 1, so it's a minor savings. OK, 2 feels pretty small, but got to check. Damn it, that was the smallest. And so selection sort, even in the best case, when the list is already sorted, is going to take at least n on the order of n squared steps because of that naivete of it. Because of that underlying design of just looking for the smallest element with no optimizations means the algorithm's always going to take us that many steps. But it doesn't have to be that way. What about bubble sort? Suppose that all 8 humans are sorted 1 all the way through 8. And here I am comparing the first two, 1 and 2, not out of order. 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and 7, 7 and 8. OK, everything looks good. And in particular, what did I not do while walking from left to right? I didn't do any swaps, so it would be foolish of me algorithmically to do any of that again, because the answer is not going to change. And so done. Took me n steps to sort n elements with bubble sort if the list is already sorted. So it would be omega of n, because in the best case, it takes you n steps. Could a sorting algorithm be constant time, or logarithmic, log n or order of 1, or omega of 1, rather? Can you sort n elements in logarithmic time or constant time? Well, what's the intuition there? These are kind of like now the fundamental meaning of computing and what you can actually do. What does it mean for me to ask, can you sort n elements in log n time or constant time? Well, that effectively is like saying, can you sort n elements without even looking at some of those elements? Right? Because both log n and 1 are mathematically, and if you don't recall, take it on faith today, less than omega of n in general. So can you possibly, intuitively, in the real world, sort n elements in some random order in fewer than n steps? Yeah? Good question. Could you make the whole list a big integer? You could, that and other tricks, but to do that, you're going to need to touch or somehow manipulate all of those values at least once to kind of do that, I would think. And so you've already spent n steps. OK, so if you have a guessing algorithm, like, yes, this is sorted, that's constant time, you're just not always correct. So I should clarify. Can you sort correctly n elements without necessarily looking at all n? The short answer is no. There is a fundamental limit of computation and also just human intuition here. You can't possibly claim to me and convince me in a court of law even that these n elements are sorted if you can't even testify to having looked at all n of those elements. It's just not possible given the computational model we've been discussing where a computer can only look at one element at a time. So sorting is out of the question, but an algorithm that takes omega of one step, for instance, in the best case, when might an algorithm need only one step? How about something like linear search or even binary search? The running time of those algorithms was big O of n and big O of log n respectively. Linear search, binary search. What's the lower bound on those two algorithms' running times? Yeah, it's omega of 1, but why? Derek wasn't so lucky, but AJ last year touched the number 50, voila, one step. And that was actually, while sort of bad pedagogy for us, was a perfect manifestation of, yes, in the best case, the lower bound on your running time might indeed just be one step or two steps, but some constant number of steps. So we have a range of these options. Now, sometimes these ranges coincide. If your big O notation, so to speak, and your omega notation, so to speak, are one and the same values, you can claim that the algorithm has a running time in capital theta. So theta just means when big O and omega are the same. You can instead use this formula and sort of convey two thoughts at once. But for now, the takeaway is that as best we've seen, for something like sorting, the best we've done so far, at least in the worst case, is big O of n squared. And this doesn't feel very good, especially since sorting and searching is all around us, right? Anyone with an iPhone or an Android, I mean, there's so much data that we're carrying around in our pockets these days, let alone in the cloud and on our laptops and desktops, that is just generally good practice to keep sorted, right? In your phone book, it would be pretty tedious if all of your friends and family were in random order in the contacts list, and you had to scroll through the whole darn list, big O of n, to find someone. No, instead we have a search box, of course, and most of us probably wouldn't blindly scroll through the whole list. But even that search box, if you start typing in DER to look up Derek or SMITH to find Smith, well, how is iOS? How is Android finding Mike Smith or finding Derek? Those pieces of software themselves have algorithms that underneath the hood are hopefully leveraging smarter algorithms than we've even seen here. Because especially as you have more and more friends, more and more family members, even big O of n squared starts to feel kind of slow, as we can see here. Let me go ahead and open up an example. So let's take a look at a demonstration. Here is a visualization that someone on the internet kindly put together. And it focuses on sorting numbers. But rather than just show the numbers textually as 1, 2, 3, 4, 5, 6, 7, 8, it instead shows them as bars. So the shorter the bar, the smaller the number. The taller the bar, the taller the number. And let me go ahead and increase the speed of this, just so it doesn't get too tedious. And let's take a quick look at bubble sort. Now notice what's happening. The two red bars adjacently are the ones that are being compared and potentially swapped. And you'll notice that just like in our human demo, what is happening over there on the right-hand side? Yeah, so the biggest elements seem to be bubbling up, if you will, to the top. Even though there's still a lot of work to be done to the left of those, we indeed have the ability here to see the list getting sorted progressively. But I'm already getting bored, right? This algorithm doesn't feel very fast. It's very pretty. It's very correct, it would seem. But it's a little slow. Let's try another one to see if it's any better than that. That's the spoiler. That's what it should look like. Let's try our friend selection sort, which is already sorted. Let me stop this. Let me click on randomize array, and now click selection sort. What's happening here? This is like me walking across the audience again and again and again and again. You don't see any of this bubbling effect, but you do see the smallest element being selected again and again and again. So we're kind of cleaning up that mess one step at a time. Still going to take some steps, but you can perhaps see it a little better and a little faster here. And spoiler alert, when we skip forward to the end, that's what it looks like. If we now randomize it one last time and do insertion sort, this one kind of feels and looks different. It's kind of mostly fixing things, but then it kind of goes in and fills in the gaps, because indeed it's moving forward one at a time, grabbing the element, and then shifting the elements as needed to make room for whatever number it's encountered. So that's why sometimes it only takes a few steps because you find where it belongs. That time it took a while to find the space that it belongs. But generally, the list is getting more and more sorted. And once we do get to the very end, this one we can actually feel being a little faster, which isn't necessarily testament to it being fundamentally better. All of these remain on the order of n squared steps. And now, indeed, it's starting to drag, kind of like our blue books. And now we're actually complete. But what if we were to compare these things? Bubble sort on the left, selection sort in the middle, and then a third algorithm that we've not seen this time called merge sort. So insertion sort's roughly the same as all of these. So this visualization lets us try 3. To start this, I have to click on them. So there's a little bit of a fudge factor here where I have to click on all 3 programs quickly in succession to see them. But let's see if we can't do fundamentally better. Merge sort is our new friend on the right. Oh my God. You know, and these are different visualizations, but they're the same algorithms. And it's not that they're just poorly implemented. It's arguably that they're poorly designed. They are all correct, but merge sort clearly seems to have some upsides over selection sort. And if you'll take on faith for now, just because we can only fit 3 on the screen, insertion sort too. You see the bigger elements bubbling up to the top. You see selecting, again, it turns out this person implemented selection sort by selecting the biggest element, but that's fundamentally equivalent to selecting the smallest element. And that's because you can see them all stacking here in this way. But my God, I wonder, can we start this again? Let's try. Let's see if we can lap it. Come on, come on, come on. Come on. Oh, so close. All right. Had I not talked as much. So merge sort, where is this magical algorithm? What are we actually doing, wasting time on these other things? Well, let's consider exactly that, but we need sort of a secret ingredient. And let me revisit Mike Smith for just a moment. So you'll recall this was the pseudocode that we had for Mike Smith in week 0, and we decided when Mike is earlier in the book or when Mike is later in the book to just go to an earlier step, thereby inducing some kind of loop. But suppose we change that language to be this instead. Don't go to a specific line number. Don't go to some earlier step. But just more generally say, search for Mike in the left half of the book, or search for Mike in the right half of the book. This is borrowing an idea that I proposed a moment ago when we were searching for something else. And what word did we ascribe to this kind of approach of this cyclical use of your own definition? Yeah. Recursion. So recursion is actually this secret ingredient that we can leverage both intuitively and in code to implement this new and improved 4th algorithm, merge sort. And indeed, this we'll use as demonstrative of a class of algorithms that doesn't behave in quite the same way fundamentally as selection sort, insertion sort, and bubble sort. Indeed, you can do better than big O of n squared. You can do much better, as you felt a moment ago with that visualization. And merge sort is one such algorithm with which we can do that. And amazingly, the pseudocode is this simple. When you're given n elements, if n is less than 2, just return, right? If you have fewer than 2 elements, the list is of size 1, which is sorted, or size 0, which is also meaninglessly sorted, so you're done. So that's kind of a base case, like a default scenario. Let's just make sure that no matter what, we eventually quit, even if the list is super small. But then the magic is hidden in those last 3 lines. Else, sort the left half of the elements, then sort the right half of the elements, which is completely punting, so to speak, just kind of recursively calling yourself. But the key detail here is that then you have to merge the sorted halves. So you're not just looking for Mike to the left and looking for Mike to the right. You're doing something on the left, something on the right, sorting each half, but then you have to kind of weave things together. And we'll see how expensive that actually is. So let's take an example. And I mock this up with some very simple animation so we could walk through it step by step. But consider the following. So here's that same list from before where we had a whole bunch of volunteers. But rather than call up humans, we'll just do this visually. Let me consider the fact that this is really just an array. So I'm just going to box everything like this. And this is actually key that we have random access to these elements. We can jump right to the elements we want, and code ultimately too if we cared. And now let's focus on the left-hand side. So I've wrapped 4, 8, 6, 2 in a solid line and left everything else dashed because I want to focus our attention on sorting the left half. So again, to rewind, this is the algorithm. And the goal at hand is to walk through visually an example whereby we sort 8 elements. And we do that by sorting the left half, sorting the right half, and then somehow merging these things together. So how do we do this? Well, let's consider the left half. All right? How do I sort a list of 4 elements? What does it mean to sort the left half? Well, what algorithms do I have in my toolkit for sorting elements? Yeah, selection sort, insertion sort, bubble sort, but merge sort. And that's where this gets weird quickly. You want to use your same algorithm to sort the left-hand side of this list, and yet we haven't even finished defining this algorithm, but that's going to be OK. We'll see. So let's sort the left half. How do you sort the left half of a list? Well, you sort a list of size 4. What does that mean? How do you sort a list of size 4? Sort the left half of that. So let's focus on 4 and 8. All right, how do you sort a list of size 2? Merge sort it. So how do you sort a list of size 2? Sort the left half. OK, beautifully. Done. Right? Done. Sort the right half. Nice. Done. I mean, I'm doing real work, or claiming to. But now I have to do something more. Now I have to merge the 2 halves. So I'm taking a step back. I have 2 lists now, one of size 1, one of size 1. I have to merge these things 2 together. Which comes first, 4 or 8? 4. So let's create some extra space for it. Let's put 4 here, and let's put 8 here. So here's a key detail with merge sort. Kind of cheating, at least at the moment. I'm using some extra space. So I hope you won't mind. To achieve this, I'm using more memory, more RAM that I wasn't allowing myself for selection sort, bubble sort, or insertion sort. OK, so now it's going to be easy to get lost quickly. So what have I just done? I have sorted a list of size 2 by sorting the left half, done, right half, done, merging it together. So now I have a sorted list of size 2. Rewind the story. What step comes next? Sort the right half that was of size 2. So if you kind of mentally buffer all of the to-dos that we're doing and then pluck them off as we go, you'll see where the story goes. Now I want to sort the right half of the original list, or sorry, the right half of the left half of the original list. How do I do that? Sort the left half, done. Sort the right half, done. Merge them together. What comes first, 6 or 2? OK, so let's give ourselves a little more memory for that. So we have a place to put it, 2, and then 6. All right, so it doesn't look like all that much progress, frankly. My left half of the list is now 4, 8, 2, 6, which is not really sorted, but we'll get there. What step comes next? I've just sorted the right half of the left half of my original list. You're missing a step. Merge, that third step. Once you've sorted the left half of something, then you've sorted the right half of something. Now you have to merge them or weave them together somehow. So the left half of the list in the story at the moment is 4 and 8. The right half is 2 and 6. So here's where you can kind of bring out your fingers to think through this sort of conceptually or in pseudocode. Here's the left list. Here's the right list, or the right half. So how do I merge these 2 together? Well, it turns out, and you can see it now. Before it was idiotic that we just were merging lists of size 1. It's pretty easy. Here now we have something substantive to talk about. So I have one list here, one list here. Which element from these 2 lists obviously comes first? So 2. And so what I'm going to do is then 2 is going to have to come down here. And then I can advance my right hand, so to speak, and now compare 4 and 6. What's going to come next? 4. Now I can advance my left hand. I compare 8 and 6. Which comes next? 6. Now my right hand, its job is done. I have only one more to do, and this. So what's key in the merging is that you essentially have this left hand and this right hand concept. Each of them kind of steps forward over time, but you never go back. You never double back. So it's this sort of linear relationship with your left and right hand as you're merging the lists together. So pictorially, let's see that. We compare 4 and 2. 2 goes first, then 4. Then 6, then 8. Where am I in the story? I mean, we've been droning on for some time now. I have just successfully sorted what? The left half of the original list, which means the next step is Sort the right half of the original list. So I can box that in to draw attention to it. How do I sort a list of size 4? Well, that's really just two lists of size 2. Let's sort the left half. How do I sort a list of size 2? Well, that's really just a list of two lists of size 1. Done. 1 is sorted. Done. 7 is sorted. Now I have to merge them together. 1 comes first, then 7. OK, now sort the right half of the original list. OK, sort the left half. Done. Right half. Done. Merge them together into some extra space. 3, and then 5. Now where am I in the story? Now I have sorted the left half of the original right half and the right half of the original right half. So now I have to merge them together. So 1, 3, 5, 7. Almost there. Now we're sort of rewinding in time. Now we're at the very first chapter in the story. Sort left half, sort right half, merge. I have that one final merge step. So what comes first from the left half and the right half? 1, 2. Even if you've lost track of the story, the answer is going to be 1, 2, 3, 4, 5, 6, 7, 8. But 1, 2, 3. But notice what's happening here. In effect, whatever code is implementing this, it's as though like my right and left fingers are just moving from left to right, plucking off the element that is indeed then the smallest. Whew. That was a heck of a lot of work. And frankly, that story seemed to take longer to tell than any of the others. But what happened? And in fact, I've left deliberately with this little animation of sorts on the screen the remnants of where we came. And it looks like I really cheated, though, right? I seem to first say, hey, I need some extra RAM, and I took it. And then I didn't mention I needed more RAM. I didn't mention I needed even more RAM. So this seems to have taken like 4 times as much total memory than any of our previous algorithms. But that's not actually the case. I left this here pictorially so we could see the history. Technically, you do need more RAM to implement this algorithm, merge sort. But we could have cut corners. Instead of merging down here, we could have just merged back into our original chunk. And so we could have just bounced between 2 separate arrays. But this is just a little more clear in terms of remnants. So how many steps did this take? Well, how many times did I divide my original list in half, in half, in half, effectively? I had 8 elements here. And that was really like if you divide it up differently, 2 bigger halves and 2 bigger halves. But if you divide it again, that's like 2 really big halves. And then you get 1 big list. So it would seem that starting here, I divided it 1, 2, 3 times. I did some splitting, left half, right half, left half, right half. And anytime you split something in half and half and half and half, what's the running time of anything involving like halving again and again and again? It's like binary search. Log n, log n. So anytime you see in computer science more generally, certainly CS50 in upcoming weeks, this division and conquering again and again and again, where you're dividing something in half, odds are logarithmic running time is somehow at play. But this algorithm, merge sort, surely cannot run in big O of log n time. Because again, you can't sort n elements in less than linear time, because you'd be guessing that everything is sorted. So log n is not the final answer here, but there is something logarithmic happening. However, even though we did a left half, right half thing, a left half, right half thing, a left half, right hand thing, sort of a total of 3 times, from here to here to here to here, at which point we were done, on every row that's on the screen, if you will, what did I do with my left and right hand? I sort of always did n steps, right? Even if you can really see it up here, how did I merge this last thing? I had to touch all 8 elements by walking through the list. How did I merge these 2 left halves? Well, I had to do this, and then I had to do this. So if you kind of consider the remnants of my fingers touching the screen, every time I did a divide and conquer, I had to touch every element in order to merge them together. So I did log n things, and every time I did that, I incurred n steps of merging. So log n things times n is going to give me big O of n log n. So this was among the options on our sort of menu of possible running times, at least that we'll focus on right now. This is bigger than log n, of course, because you're multiplying it by n. But it's smaller than n squared, because if log n is less than n, then surely n times log n is less than n. And so the running time here of merge sort is indeed going to be big O of log n. Any questions on this here? All right, if I may, let me point out one other approach for seeing this same thing as follows. You can actually glean this kind of detail more formally, especially if you're the mathy type, from the pseudocode itself. We didn't have to walk through this whole verbal exercise or visualization thereof. What if we just go back to basics and just analyze our own pseudocode or our own C code eventually, line by line? So here's the original algorithm. How many steps does this take to just check if n is less than 2, return, we're done? Big O of what? It's just one step. Or maybe it's 2, like the if and then the return, but it's constant. It's 1 or 2. We can debate that, but it's constant. It has nothing to do with the size of n. You're just making a finite number of decisions there, 1. So you know what? The running time, which I'm going to formulaically say is t of n. So the running time when your input is of size n, is just going to be like on the order of constant time, big O of 1, whenever n is less than 2. This is not a very bold claim. It's sort of like I'm plucking off the easiest part of the question, but it's at least correct. If you have a small list, it's constant time. The harder question is when we analyze the rest of the algorithm. How many steps does it take to sort the left half of elements? How many steps does it take to sort the right half of elements? And how many steps does it take to sort, to merge the sorted halves? So we have 3 questions to answer. And let me propose this. You can kind of punt, and this is the beauty of recursion. You can sort of answer the question with the question. The running time to sort n elements is really the running time to sort n over 2 elements, the left half, plus the running time to sort n over 2 elements, the right half, plus the merging step, which I claimed per my sort of left-right finger intuition is big O of n steps, linear. And now this holds if n is greater than or equal to 2. Now, unfortunately, this is like a recurrence, if you will, mathematically. This really is a cyclical definition. We really need to be able to generalize this and explain it a little more formulaically. But indeed, take a guess. If you have like your old physics textbook or your math textbook, what does this recurrence actually equal if you multiply it all out and prove it mathematically? What's the running time total of something where you do some function of n over 2 plus some function of n over 2 plus some number of linear steps where each of those inner running times is recursively defined, right? And that's just to be clear, the reason this is like non-obvious and should be kind of over most heads, at least if you're less familiar with this world, is that I'm saying that the running time t is a function of the running time t. Like, again, that's answering a question with, defining a word with the word itself. But it turns out there are ways to prove this inductively, mathematically. And indeed, if you actually multiply this all out in your textbook, you will get something on the order of n times log n. So where has that left us? We've introduced a whole number of algorithms here, the last of which, merge sort, gives us this ability to actually solve problems much faster than any of the others. But in each case, are we able to apply some general formulaic analysis, asymptotic notation, so to speak, big O, big omega, and big theta, that describes in general terms how much time these kinds of things take. So let's now translate one of today's key ingredients to actual C code so that we can see how we can leverage this programmatically. So here in CS50 IDE, I've got an example, sigma 0 and sigma 1, both of which at the end of the day do the same thing, but they do it differently. And in sigma 0 here, we have the following code, a sigma function that takes as input an integer, m, as its sole argument, and it has a return value of type int, so it's going to return a number. Main takes no command line arguments, so no argv, no argc this time. But inside of main is code that's going to pester the user again and again until he or she gives us a positive integer as per this condition down here. And then notice down here, I'm going to call a function sigma, passing in whatever the user's input was, 10 for instance, or 11, or some other value, storing the answer in answer, and then just printing it out. And what's nice about the fact that, frankly, you can't see anything else on the screen is that for all intents and purposes, sigma, the function at the moment, is a black box. It is a function whose purpose in life is to add all the numbers from 1 up until the user's input and return it. And we don't know yet or need to care how it's actually implemented. If we do take a look inside that black box, down lower in the file, you'll see this code here. Sigma takes an input m as an int, returns an int. And what does it do inside? Well, I've got like what I'll call a counter variable, called it sum, initialized it to 0, and then using a for loop, iterating from 1 up to m, because I want to sum all the numbers from 1 up through the value the human has typed in. I just want to keep adding to the sum that value. So it's not just sum plus plus. If I did sum plus plus, as we keep seeing syntactically in examples, that would just add 1. I want to add in whatever I is, whether it's 1 or 2 or 3, as I'm counting all the way up through the user's input and then I return sum. But the neat thing about sigma is that it affords an opportunity for recursion. This isn't necessarily a better opportunity or more correct, but we could view the world a little differently. Sigma1.c is identical code in main, but the implementation of sigma is fundamentally different. And here's where it's kind of mind-blowing, at least at first glance. You can implement a function like sigma in such a way that the function calls itself. Much like the running time for merge sort is defined in terms of itself, much like searching or sorting a list can be recursively defined as searching or sorting a smaller list, but with the same steps, we implement this code in C as follows. On this line here, if m is less than or equal to 0, it's really just a sanity check. If the human was messing with me and somehow was able to inject a negative value or a 0 value into this function, I don't want to get stuck in some random like infinite loop. I want to catch that. So I'm just going to say less than or equal to 0 just to be super defensive when programming, return 0. Like it's not correct to say that, but I just want, and I'll document this in my comments, for instance, return 0 if the user does not cooperate. I need that base case so that stuff stops eventually. And then here's kind of the amazing thing. In my else condition is one line of code that implements the entirety of this function. The result of asking me the question, what is sigma of m, is really the same thing as saying m plus sigma of m minus 1. In other words, if the goal is to count up all of the numbers between 1 and m, logically that's the same as counting up all the numbers from m to 1. And so if I view it that way, if you give me m, I am going to sort of on my cheat sheet write down the number m and then say plus whatever the summation is from m minus 1 all the way down to 1. And you know what? I have a function, a piece of code that gives me exactly that answer if I just pass in that slightly smaller value. So on first glance, it might look like sigma calls sigma. That can't possibly be a good thing. But it doesn't do it forever. Sigma might call sigma, might call sigma, might call sigma. But at what point in the story does sigma stop calling sigma? When it's counted, when m, the input, is what? Negative, or we shouldn't hit negative ever. We should first hit 0. So once m minus 1 gets so small, 1 minus 1, that it equals 0, this line of code is going to kick in, and it's going to say, return 0, thereby short-circuiting this seemingly infinite loop, which does, in fact, terminate eventually once the input gets small enough. Now, probably you shouldn't bother implementing code like this. If anything, we'll talk about this in future weeks. Calling function after function after function after function after function actually can take up a lot of memory. It can actually cause your computer to crash in some cases, and we'll talk about when and why. So this isn't necessarily the best technical decision, but it's illustrative of the capability we have in programming to map intuition from like our binary search or our merge sort into actual code. And indeed, there's going to be data structures that we soon see, far fancier than arrays. We're going to see things like linked lists and trees and tries and hash tables and yet other data structures still that are going to allow us opportunities to implement algorithms on top of those data structures, so to speak, to answer questions using an ingredient like this one here. But of course, we're left then, fortunately, with a better algorithm than something like bubble sort. And indeed, this is fairly well known now, it would seem. And I thought we'd conclude with a look at this interview that was conducted with a certain senator some years ago who was running for the presidency and was asked by Google's own Eric Schmidt, the CEO at the time, a set of interview questions, one of which we thought was appropriate note to end on here.
Now, Senator, you're here at Google, and I like to think of the presidency as a job interview. Now, it's hard to get a job as president.
Right.
And I mean, you're going through the rigors now. It's also hard to get a job at Google.
Right.
We have questions, and we ask our candidates questions. And this one is from Larry Schwimmer.
Okay.
What? You guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no. I think
that's not a.
I think the bubble sort would be the wrong way to go.
Come on, who told him this? Okay. I didn't see computer science in your background.
We've got our spies in there.
Well,
All right, so that's it for week 3. We will see you next time.
So you want to know the full story, huh?
As far back as you can remember.
All right, well, let me tell you. First time I met David Malin, I knew he was nothing but trouble.
There's a David J. Malin here for you.
Who?
He says he's in your Computer Science 50 class, wants to talk about his grade.
You kidding me? I mean, who does he think he is? Bill Gates? All right, send him in.